All right, so buckle up, folks, because today on the deep dive, we are going deep, really deep.
Deep.
Yeah, into the heart of a cosmic puzzle that could rewrite, well, kind of everything we thought we knew about how the universe ticks.
That's right. We are talking about dark energy and the very real possibility
Yeah.
that it might not be the constant force we've always assumed it to be.
Right, exactly. Like, we are talking about a potential paradigm shift here, folks, and we are diving deep, like deep into the latest findings based on some incredible data coming out of the Dark Energy Spectroscopic Instrument, or DEAI.
Yeah, DAI, incredible project.
I mean, this thing is a beast, right?
Yeah.
It's mapping millions upon millions of galaxies across the universe
It really is.
to get a handle on this whole dark energy enigma.
Exactly.
And the analysis we're looking at today, this uses 3 years worth of data, something like nearly 15 million galaxies and quasars.
Yeah, 15 million. It's just an incredible amount of information giving us, a look into the structure of the universe and how it's been expanding over time.
Like a cosmic time machine almost, right?
Yeah, you could say that.
So for everyone listening, our goal today, our mission, is to unpack this, right? To unpack what these findings could mean, why they have scientists so excited.
And why this idea of a changing dark energy would be kind of a big deal.
A big deal. I mean, it could shake up the standard model of physics.
Exactly.
So before we go any further, let's just let's talk about DSI itself, right? What is it and what makes it so special?
So imagine you're trying to solve a cosmic mystery.
Okay. Oh, good mystery.
So to solve this mystery of dark energy, scientists have built this incredible detective tool, and that's DESI. It's designed to study dark energy by mapping these distant galaxies.
Distant, we're talking billions of light years away, right?
Right, and it's meticulously recording the locations and distances of these galaxies.
Like a cosmic census.
Exactly, a cosmic census on a grand scale.
And where is this incredible machine located?
It's installed at the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory.
Kitt Peak.
Yeah, in Arizona.
Beautiful place.
It is, and we actually have a stunning image of the telescope here under these amazing star trails. Credit for the photo goes to KPN Anwar Lab and Sfarab.
Tafreshi.
I've seen it. It's breathtaking. It's just, it just gives you a sense of the scale of what we're dealing with here.
It does. And DSI, it's not just pretty to look at. It has some really impressive capabilities.
Like, how impressive?
Well, it can capture light from an incredible 5,000 galaxies simultaneously.
5,000 at the same time.
Yeah, at the same time, it uses robotic positioners to aim fiber optic cables at each galaxy.
Whoa.
And that's how it gathers so much data in a single night. Massive parallel data acquisition.
I mean, that just blows my mind, the technology involved and the sheer amount of data.
It's incredible. And the overall goal, by the way, the ambition of the project, is to measure something like 50 million galaxies and quasars.
50 million, by
the time the survey is finished.
This 3-year analysis with almost 15 million objects, that's a huge step towards that goal. It is, and it just speaks to the scale of this whole undertaking.
It's a massive collaboration.
It is a global effort.
And I know there are a lot of institutions involved supporting this project.
Yeah, definitely. So we have major support from the Department of Energy, or DOE,
Yeah.
Office of Science,
Okay.
National Science Foundation, or NSF, and a whole bunch of international partners.
So a real global team effort.
Yeah, and the DOE's Lawrence Berkeley National Laboratory, they manage the whole experiment.
Got it. And also important to remember that all of this amazing research is happening on Iolcum Duag,
Yes.
also known as Kitt Peak. And this is, a site of huge cultural importance to the Tano O'odham Nation.
Absolutely. And the DSI collaboration, they operate with deep respect for the privilege of being able to work on this land.
So that's D as I.
Powerful instrument.
So mapping the universe.
And mapping the universe.
On a scale we've never seen before. But the big question is,
Yes.
what's it telling us?
Right. So the exciting news, and the reason we're doing this deep dive today, is that this analysis of 3 years of DEI data, well, it's hinting pretty strongly that dark energy,
Might not be the constant force we thought it was.
exactly, it's suggesting it could be evolving, changing over these vast cosmic timescales.
Which is mind-blowing, right? Because
It challenges this long-held idea of a fixed cosmological constant.
a constant force that's been driving the universe's expansion.
And it might not be so constant after all.
I mean, that changes everything.
It really does.
And this isn't just like a wild guess, right?
No.
This is based on data, and it's building on earlier hints, too.
Yeah, so if you go back to April 2024, Dr. Mustafa Ishaq Boushaki, He presented the initial analysis of DESI's first year of data.
At the American Physical Society meeting.
Right, and even then there were these tantalizing clues.
Early signs.
That dark energy might be evolving.
And now with 3 years of data, those signs are just getting stronger.
Much stronger.
So let's talk about Dr. Mustafa Ishaq Bushaki for a minute. Who is he? What's his role in all of this?
So he's a physics professor at the University of Texas at Dallas.
Okay.
And he's also the co-chair of the DSI working group that's tasked with interpreting all this complex cosmological data.
So he's leading the charge in figuring out what all this data means.
Exactly. We actually have a photo of him here, courtesy of the University of Texas at Dallas.
Oh, cool.
And it's important to remember, he's not doing this alone.
Right. It's a huge collaboration.
Yeah, the DSI collaboration, it's over 900 researchers.
Wow.
From more than 70 institutions all over the world.
So a global effort to understand, one of the biggest mysteries in the universe.
Yeah. Exactly.
All right, so let's get into the nitty-gritty here. If dark energy is really weakening, what's that actually mean for the universe?
Well, it could mean that the universe's expansion, which we've always thought was accelerating, well, that acceleration might be slowing down. Compared to what we'd expect with a constant dark energy.
Okay, so the universe is still expanding, but maybe not as fast as we thought.
Yeah, and the exciting thing is, the evidence for this, it's not just coming from DSI.
Right.
There are other independent cosmic measurements that seem to support this idea.
Like what kind of measurements?
Well, there's data from the cosmic microwave background.
The CMB, that faint afterglow of the Big Bang.
Exactly. And then there are observations of supernovae, these exploding stars that we use to measure cosmic distances.
Like cosmic mile markers?
Yeah, you could say that. And there's weak gravitational lensing, which is kind of like...
I've heard of that, but it's always a little confusing.
Imagine looking through a warped piece of glass. The images behind it would look distorted.
Okay, yeah.
And gravity from large structures in the universe, it does the same thing to light from distant galaxies.
Bends the light.
Exactly. And by studying that bending, we can map out the distribution of this, invisible matter. And when you put all that together, the DSI data, the CMB, the supernovae, the lensing...
It paints a pretty compelling picture, right?
It really does. And it all seems to point towards this idea of a weakening dark energy.
So multiple lines of evidence, all converging on the same conclusion. I mean, that's pretty powerful, but
yeah.
I know physicists, they have a really high bar for claiming a discovery. So where do these findings stand in terms of, statistical significance?
Right, that's an important point. So while the evidence for evolving dark energy is strong, and it's definitely exciting, we haven't quite reached that gold standard of 5 sigma.
5 sigma, that's like the holy grail of physics, right?
It is. It means there's less than a 1 in a million chance that what we're seeing is just a fluke random chance.
So we're not popping the champagne corks just yet.
Not just yet, but the current significance, when you combine DSI data with all those other measurements, it ranges from about 2.8 sigma to 4.2 sigma.
Depending on which data sets you're using.
Exactly. So it's a very strong signal, but not quite a slam dunk.
Okay, so we're getting closer.
We're getting there, and Dr. Ishaq Bushaki, he's pretty optimistic.
I remember reading that quote.
Yeah, he said, with a 4.2 sigma significance, I think we are getting to the point of no return.
He seems pretty convinced.
He is. And he's not just excited about confirming those early hints, from the first year of data. He's also excited about the fact that the statistical significance is increasing.
As more data comes in.
Exactly. And the fact that this evidence is showing up across different data sets, that's really important too.
Why is that so important?
Well, it makes it less likely that we're just seeing an error or an artifact in a single experiment.
Makes the findings more robust.
Exactly, more robust. And you can really sense his excitement about this. He's been studying cosmic acceleration for 25 years.
This is like his life's work.
It is. And he really believes that if this evidence continues to grow, as he thinks it will.
With more data coming from DESI?
Yeah, then this will be huge for cosmology and all of physics.
Huge?
Huge. Those were his words.
So we've talked about DESI mapping millions of galaxies, but can you just give us a sense of, how massive this map of the universe really is?
It is massive. DSI has created the largest 3D map of the universe that we have to date.
Largest ever.
Ever. They've essentially taken a snapshot of the cosmos.
Wow.
And each of those almost 15 million galaxies and quasars, each one is a point in this vast three-dimensional map.
I'm trying to picture this. It's mind-boggling.
There's actually an animation that shows this. Starts with Earth at the center.
Okay.
And then all these points stretching out billions of light years in every direction.
I've got to see that.
It's incredible. Credit for the animation goes to the DSI collaboration and KP&OR Labs Fowler Proctor.
And this map, this cosmic census on steroids, it's the foundation for everything they're trying to learn about dark energy.
It is. By studying the distribution of these galaxies, how they're clustered, scientists can piece together the history of the universe's expansion.
And figure out what role dark energy has played in all of that.
Exactly, over billions of years.
Yeah. So let's imagine for a second that these hints, these clues, they turn out to be true. Dark energy isn't constant, it's evolving. What does that mean for our understanding of the universe?
Well, it would mean we'd need to revise our current model of physics, the standard model.
The standard model, that's like the bedrock of physics.
It is, and right now it incorporates a cosmological constant to account for dark energy.
A constant?
Yeah, but if dark energy isn't constant, then that part of the model needs to change.
We'd need new physics to explain it.
We would. It could point to the existence of new fundamental field or maybe new particles or even forces that we're not aware of yet.
Like completely new stuff that we haven't even imagined.
Exactly. It's pretty mind-blowing.
It would be a revolution in physics.
It would, and it would open up so many new avenues for research, new questions to answer.
About the universe, about reality itself.
It would change everything.
So, to sum it all up for our listeners, new data from the Dark Energy Spectroscopic Instrument, DEA, this incredible project that's mapping the universe on a scale never seen before, well, it's giving us strong hints.
Strong hints.
That dark energy, this mysterious force that's been driving the universe's expansion, it might not be the constant we thought it was.
And while we haven't quite reached that gold standard of 5 sigma for a definitive discovery, the evidence is mounting. And it's coming from multiple independent sources, which makes it even more compelling.
It's a really exciting time to be following this research, and with DESI continuing to gather data, well, who knows what we'll discover next.
It's a cosmic mystery that's just starting to unfold.
And it could change everything we thought we knew about the universe. Thanks for joining us for this deep dive, folks. We'll be back with more mind-blowing explorations of the cosmos soon.
See you next time.
Bye.